Hello everyone and welcome to this new video. In particular, this will be the fifth video that will be part of a series about abstract algebra. And we remember that in the last video we viewed some more examples of the structure of a group, in particular the general and the special linear group, as well as also the multiplicative and the additive group modulo n. So now we are ready to proceed with the theory, considering that we could say we got our hands dirty quite a lot with working with examples. So now we have enough intuition to proceed with the abstract theory. And we will start this video by proving the following fact about groups in general. And that is, so let G under a operation that we just denote by this little dot here, and we will just use product notation. So if we say like A and B under this operation, we just denote it by A times B. So let G be a group. Then we have that the following properties hold. In particular, if we have, so let E be the identity of the group. We use this notation here. We used it already in the last videos. And so if we have that A and B are elements of G, if we have that A times B is equal to the identity, then we necessarily have that B is equal to A to the minus 1. In other words, inverses are unique, where here A to the minus 1 is actually one of the inverses. Before we actually proved that they are unique. So the second property that we will prove is that if we have, well, an element, the inverse of an element is just the element itself. And the last property that we will prove is that if we have A times B and we take its inverse, just equal to B to the minus 1 times A to the minus 1. So these are three facts that we will prove. So let's prove it. Okay, so for the first one, we know that A times A to the minus 1, that is equal to A to the minus 1 times A, is equal to the identity. Now we also have that A times B is equal to the identity. So we now want to find an expression for B. What will be? B, well, by the definition of identity, B is just equal to E times B, where we multiply E on the left. Now, E, by this observation here, is just equal to A to the minus 1 times A. So we can have that this is A to the minus 1 times A times B. But now, by the associativity of the product in a group, we can say that this is equal to A to the minus 1 times A times B. But A times B is precisely the identity. And what we have now is, by the definition of identity in a group, that this is all equal to A to the minus 1. So what we have obtained that, so we have supposed that A to the minus 1 is one of the inverses of A. Now we have supposed that B is another inverse that we do not know if it's equal or not of A, and we have obtained that, well, yes, B is indeed is equal to the inverse A to the minus 1 that we took at the beginning, and so we have that, yes, inverses are unique. And that's the first thing proven. So now for the second one, it is actually rather simple. We just noticed that, well, A to the minus 1 times A is equal to A times A to the minus 1 is equal to the identity. And now by the uniqueness of the inverse that we have proven in the last point, plus this relation here, we notice that A acts as precisely the inverse of A to the minus 1. So we can say that the inverse of A to the minus 1 is just A. And so this proves the second point. And for the third point, we have that, well, we want to find that relation for A times B to the minus 1. So now, we start by observing that A times B to the minus 1 times A times B is equal to the identity. Now multiplying by B to the minus 1 on the right, both sides, we get that A times B to the minus 1 times A is equal to B to the minus 1. And now multiplying both sides to the right by A to the minus 1, we get that A times B to the minus 1 is equal to B to the minus 1, A to the minus 1. And this concludes the last fact, and this concludes the proof in general. So now we will also to prove this very fast corollary. This is an immediate corollary. And well, if we have A times A1, A2, A3, up to AN, that are elements of a group, and if we take the inverse of A times 2, of A1 times A2 up to AN, so we take the inverse, then we will have that this will be equal to A to the minus 1 times A to the minus n minus 1, up to A1 to the minus 1. So how can we prove this? We can prove it by induction. So we have already covered the base case, n equals 2. So now suppose that it's true for n equals k. So we have that for n equals k, a1 dot 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 up to ak to the minus 1 is equal to a to the k minus 1, a to the k minus 1 to the minus 1 dot 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 up to a1 to the minus 1. So if that is the case, now we will, for the induction step, we want to prove it for n is equal to k plus 1. And now the proof is rather straightforward. In particular, we have that a1 times a2 dot 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 times a to the k plus 1 to the minus 1 is nothing but, well, writing it in equivalent ways, just a1 times a2 dot 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 up to ak times ak plus 1 all to the minus 1. And both, of course, are elements of G by the closure of the operation that we have as a group axiom. And from this, and using the property that we already proved above, that is a times b to the minus 1 is equal to b to the minus 1, a to the minus 1, we can write all of this as a times a to the k plus 1 to the minus 1, all times a1 dot 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 up to ak all to the minus 1. And now, by using the induction step above, so this supposition that we made here, we have that our result is ak plus 1 to the minus 1, ak to the minus 1, all until a1 to the minus 1. And this concludes the proof for this very simple induction proof. And now we move on to prove some other facts. So now let us prove some other facts. This time we will prove some facts about abelian groups. So we start by the following, and that is, let G be a group again. So let G be a group. Then we want to show that if for all x in G, we will have that the order of x is 2 or x squared is equal to the identity of our group. And so note that here E comes from German, like most, you could say symbolic notations in mathematics, like Einheit, that means Einheit, which is unity. As I was saying, like for example, the integers is Zahlen, which means integer in German, and many other words. So just for an historic note here. So if we have that for all x in G, then x is order 2, then we will have that G is an abelian group. In other words, it is commutative. So let's prove it. So here we can prove. So the proof of this fact is rather simple and follows from two observations mostly. So let's suppose that x and y are elements of G. Then we know that all elements have order 2. So in other words, we will have that as a consequence of that, x squared is equal to the identity, y squared is equal to the identity, but also, of course, by the closure of the multiplication, we'll have that xy and yx will be elements of G. And we will have that also they will have to be equal to the identity when squared. So they have order 2. So now, this is the first observation. And the second observation is that if x has order 2, then x is its own inverse. So every element of G is its own inverse. And consequently, x times y to the minus 1 is going to be equal to x times y, and y times x to the minus 1 is going to be equal to y times x. So with this in mind, what we want to show is that x times y is equal to y times x. In other words, the group is abelian. How can we do that? So we start by x times y to the minus 1. By the property we proved above, in particular this one, we have that this is equal to y to the minus 1 times x to the minus 1. But remember what we said before, all elements are their own inverse here. So we have that this is equal just to x, y times x. So this is the first identity that we have. Now we notice a second thing, and that is that y times x to the minus 1 is going to be equal to itself, because because all elements are their own inverse. Now, by another property that we proved above, we know that the inverse of an inverse is itself. So the inverse of x times y is just x times y. But remember that the inverse of x times y, we said above, is y times x. So this is the inverse of y times x, but the inverse of y times x is precisely y times x. So we have reached to the thing we wanted to prove, and that is x times y is equal to y times x for all xy in G. So G is a abelian group. And so we have proved this fact. So now I want to prove another fact about abelian groups, and that is that a non-abelian group necessarily has order greater than 4. We can actually say necessarily order greater than 5, but that will, I think it's better that we prove that once we prove Lagrange's theorem. And for now, let's not worry about it. So for now, let's just prove that a non-abelian group necessarily has an order greater than 4. So let G be such group. Now, in order for it to be non-abelian, we would want ideally that there are elements x, y in G such that of course they do not commute, so x, y is not equal to y times x, while both are, however, members of G by the closure axiom, of course. So now, in order for the supposition that we made, we already assumed that our group has at least two distinct elements x and y, and an identity that we call as usual E. So now we want to see, in order to show that this group must have an order at least equal to 5, that x times y and y times x cannot be one of these elements. So how can we do that? So, well, the possibilities are actually 3. So the first one is that one of them is equal to E, and maybe the other one can be different, but then we will have 4 elements. So, or that one of them can be equal to y or x. So let's start by E. So if x times y was equal to E, then by the uniqueness of the inverse, we will have that y is equal to x to the minus 1. But that will imply, of course, the commutation between the two, and so we will have that x times y will be equal to y times x, that will be equal to the identity, and this is not what we want. So in this case, we will have that, of course, the group will be commutative, so it's not possible to have that x times y equal to E. So let's now suppose that, well, x times y this time is equal to x. So what happens? Well, if x times y is equal to x, then we will have that y is equal to the identity. And what would that imply? That would imply that x times y will be equal to y times x, that will be equal to, well, x. And this is again not what we want. And you can quickly see that if we say, well, x times y is equal to y, then we will have that x is equal to the identity. So again, x times y will be equal to y times x, will be equal to an identity, and this is again not what we want. So necessarily, we will have that x times y and y times x will have to be distinct elements of our group. And our group in particular necessarily has order at least equal to 5. And so this concludes our proof. So as I said earlier, we can also prove that an order of a group of order 5 is abelian, but we will wait to prove this until we have better machinery to make the proof way easier, so we will wait a little bit. Let us prove another very important property of groups that is called the cancellation property, that you have most likely employed a lot of times in your mathematical career before abstract algebra, especially working like with real numbers, etc. And that is, we have that if we have a group G, as usual, we call it G, and we have elements A, B, and C in it, then the laws of cancellation, and in this case, if it's not abelian, let's be careful about left and right cancellation, that you pretty much got accustomed to while working with real numbers. So in particular, if we have that B times A is equal to C times A, then B will be equal to C. And similarly, if we have that A times B will be equal to A times C, then again, B will be equal to C. So these two holds. And to prove this, it's very simple. So let's take B times A. So if we have that B times A is equal to C times A, then we know that the inverse of A that is unique is A to the minus 1. So we denote it like this as usual. By multiplying both sides by A to the minus 1 on the right, we will get that B is equal to C, quite simply. So this yields the first one. And for the second one, we proceed similarly, just multiplying A to the minus 1 on the left. And this again yields B is equal to C. And this proves it pretty quickly. So with this said, we have proved a good amount of results about groups. And now we're ready to give some more definitions about groups that we will use in the following videos. That will be quite important. So let us start with a definition that you are already accustomed to, but as I promised, we would have given a little bit more carefully, and that is of the order of an element. So again, let G be a group. Then we say that an element A in G has order n if A to the n is equal to the identity. And so we usually denote the order of an element as order of A, or sometimes or with this other symbol here. So it's literally the same. It's up to you to use whatever convention you like the most. So as an example, we already mentioned it when we talked about dihedral groups. Reflections S in dihedral groups are all of order 2. So we know that squaring them, actually here S is not just the reflection you remember about, for example, that point here, but it's any sort of reflection, also the ones that we obtain with by composing rotations and reflections. So every reflection has order 2. So now, as a kind of mini exercise, try to find the following orders. So find the order of the rotation R in the dihedral group dn, where remember R is the rotation by 2 pi over n radians. So find the order of this element. Also find the order of R to the 7 in D15, and try find the order of 3 in, well, U20. So try working on these 3 micro exercises that certainly help build confidence with the idea of well, order of an element. So now we will give another very important definition, and that is the definition of a subgroup. So we say that a set, actually, let G be a group. So if we have that V is a subset of G, in other words, V in symbols, then if V forms a group with respect to the same operation that G formed it, so let's call it this little dot, then V is called a subgroup of G. And we write sometimes that V with this thing that looks like the less than or equal to sign. And there's tons of theorems, useful theorems about subgroups. We will prove a couple of them that will help us determine whether a subset of a group is a subgroup or not. So the first one, so theorem, I will call theorem 1, is so the first one that we will prove is a procedure that will allow us to determine if an element is a subgroup or not in just one step. And let's state that here. So if G is a group as before, and V is a non-empty subset of G, so a subset not equal to the empty set, so we will have that if for all AB in our set V, we will have that A times B to the minus 1 is in V, then V is a subgroup of G, using the notation we defined above. So let's prove it. Now, remember that in order for something to be a group, we wanted 4 axioms, of course: closure, associativity, the identity element, and of course the presence of an inverse. So let's check every single one of them. So the associativity follows immediately from the fact that, of course, if we restrict an operation to a smaller number of elements, it will still remain associative because it does not depend on that. Well, what about the identity? Well, notice that we said for all A and B in V, we will have that A times B to the minus 1 will be in V. So if we set A is equal to A and B is equal to A, then we will have that A times A to the minus 1, which by the group axioms is equal to the identity, will be equal to V. So the identity, all under the operation that is unique, of course, as we proved before. So the unique identity of the operation dot, under which G forms a group, is a member of V. So V contains the identity. So what about the inverse element? So we saw that E is an element of V. But knowing this, we now know that since for all a and b in V, a times b to the minus 1 is in V, then if we set a is equal to E, so the identity, since we now know that it is an element of V, then we will have that E times b to the minus 1 is in V for all b in V. In other words, every element, the inverse, so every element b of V has an inverse in V. So it lies in V, and so we also satisfy the inverse element property. So the last thing that we want to satisfy is the closure. So now suppose we have A and B in V. Now, by putting B is equal to b to the minus 1, since we know that b to the minus 1 is in V, since the inverse of every element of V lies in V, then we know that A times b to the minus 1 is in V. In other words, A times B is in V. So the operation is closed. And so we have concluded our proof. So indeed, V is a subgroup of G under this dot operation. Nice. And there's actually another theorem which is still allows us to determine whether a subgroup, whether a set is a subgroup of a group or not. And this time it allows us to check it in 2 steps, and we will prove this too. And so now, again, using the same notation as before, so G for the group and V for the subgroup, we will have that if AB, if for all AB in our set V, that is a subset of a group G, we will have that A times B is in V, and for all A in V, we'll have that its inverse lies in V, then V is a subgroup of G. So let's prove it. So we already have 2 properties checked. That is the closure, because for all A and B, we have that A times B is in the group, so the closure is checked. Well, the inverse element property is checked because every element of V has an inverse that lies in V. Associativity, for the same considerations as before, is checked. We only have to check for the identity element, but this is trivial because well, we know that for all A and B in V, A times B lies in V. But if we pick B to be equal to A to the minus 1 that we know lies in V, we will have that A times A to the minus 1 will be in V, but this is precisely the identity element, and so we have proven that V is a group, in particular a subgroup of G. So with this said, I think we can stop this video here, and in the next video we will prove some more results, give some more definitions, and also give some examples of subgroups, because we didn't give many examples of subgroups, actually no examples at all in this video. So with this said, I will conclude this video here.